Alright, this is a video about example 1 from class for series solutions to ordinary differential equations. So the first thing we check, the coefficient of, we'll call this the derivative term, in quotation marks, is 1, so we don't have to worry about that. So the next thing we're going to do is the most important, to make it a series solution, right? As we're going to write all of these terms on the left as infinite series. So obviously this is the first derivative, so that's the sum from n equal 1 to infinity of Cn and x to the n minus 1. And then we have plus 2y. Y is just the function, so it's the sum from n equals 0 to infinity of c sub n x to the n, and that's all equals 0. Now notice this is a boundary value problem because we're given a boundary condition, but we'll deal with that at the end. I'm going to bring this 2 inside because ultimately that's going to make it easier. And from here, the next thing we need to do is reindex and correct for the reindexing. So obviously, I want everything to line up with just an n. It's going to be easiest to just have an n for the powers. And then I want the starting index for the sums to be the same, so I can ultimately combine them. So if I do that, I'm going to subtract 1 here, and then I'm going to add 1 to the n. Anywhere I see an n inside of the first sum, I'm going to add 1 to it. So if I do that in one step, and do it in 2, I'm just going to do it in 1. This just becomes the sum from n equals 0 to infinity of c sub n plus 1 times n plus 1 x to the n, right? And we're going to do nothing to this over here because it already has what we want. And from here we can go ahead and combine this into a single infinite series where I'm going to pull out x to the nth power. I'm going to just factor that out. And we're going to use the implication that in order for everything to be 0, this all has to be 0. So I can use that to find my recurrence relation, right? Maybe we can say that c sub n plus 1, remember it's recurrent, so we want the largest n plus whatever. It's just going to be negative 2 cn over n plus 1. And that is the recurrence relation we're going to have. So now that we have found that, I'm just going to draw a table and test a few values of n to see what c sub n plus 1 is, and we'll look for a pattern from there. That's the easiest and most straightforward way I find to do this. So I'll just say n, c sub n plus 1, right? We'll just give some space, 0, 1, 2, 3. Alright, so when n is 0, c sub n plus 1 is just c1, and this is negative 2 c naught over 0 plus 1 is just 1. So there's c1, right, for n equals 0. And then when n is 1, we get c2 is equal to negative 2 c1 over, what's that, n plus 1, so it's going to be over 2. But we found c sub 1 up here, so this is really just negative 2 over 2 times negative 2 over 1 c naught, right? And we're beginning to see a pattern in the denominator. That's positive. And we'll see what that looks like as a power series eventually. And then when n is 2, we have c3 equals negative 2 c2 over, it's the same thing down here, 3, but this is just negative 2 over 3 times negative 2 over 2 times negative 2 over 1 c naught. Exact same story down here, right? This should be very familiar by now. We see the pattern. So obviously, on the denominator, we have a factorial, right? Each time n goes up, we get something that increases by 1 as an integer on the bottom, right? So if I want to write a power series solution, I'll find the solution y is going to be equal to the sum from n equals 0 to infinity, right? And if we use these for a c sub n, well, we're just going to get negative 2 to the nth power over n factorial, right? Because negative 2 is consistently in the numerator of all of these terms, right? So we have to put the negative 2 quantity in parentheses. And then we have x to the n here also. And I can combine this, and I will, but first I want to go back to the boundary condition we were given. this says that y naught is equal to 1. So for us, what this is going to mean is there just is going to be a 1 here. We don't have to worry about anything special. This is a really easy boundary value problem. So we know that y, I'm just going to rewrite it, is just the infinite series from n equals 0 to infinity of negative 2x to the nth power over n factorial. And that is the series solution for this boundary value problem.